Hello everyone, my name is suman purbia from group 316. Here is my topic non-linear dynamics of the membrane. It is an non-linear properties of excitable membrane are distinctly manifested in a generation and a propagation of a nerve impulse. Let us consider a periodic changes in a state of a membrane established in a number of experiments. For instance, there are an observed oscillations of electrical potential in a very thin polyelectrolytic bilayer membranes. The bilayer is consist of a polyacids and a polybase. Thus, it can have three zones. First, a negative zone, a neutral zone, and a positive zone. uh, you can see in this diagram also there is a negative zone, positive zone, and the neutral zone. The membrane was placed in a point 0.5 0.15 m solution of an NaCl. When the negative potential was applied, a periodic impulses spikes were observed on the side critical value of a current there was observed. Undamped oscillation was penetrated for the hours. The current through the membrane consists of a movement of a cation through the zone A and the anion through the zone B. As a result, NaCl is accumulated in a central neutral zone. The increase of the osmotic pressure leads to a appearance of the flux solvent into a membrane and increase in a hydrostatic pressure. At the same time, the increase of a salt concentration caused the polyelectrolyte membrane to compress, which also increase the pressure. When these increase exceed the osmotic pressure, the solvent flux changes its sign and the salt concentration inside the membrane also increases even more. As the concentration gradient rises, the salt leaves the membrane and flows out of the membrane, attain the maximum concentrations. This is followed by a relaxation. The membrane returns to the initial state and the process start again. You can see in this diagram we have a different regions like A, C, B, D or ABCD. This is the diagram of the oscillation of the concentration in a coupled chemoosmotic system. Uh, let's see the torinal membrane oscillators. It is found in a 1955. It consists of a two cell filled in an electrolyte of a different concentration and separated by a porous glass membrane containing bound negative charges. When a direct current is passed, a potential difference is created on the both side of the membrane, and the shift in a liquid level arises in the cell. At high constant current, periodic oscillators in a liquid level and in the membrane potential occurs in the system. Because of the presence of a negative charges in the membrane, the electrolyte in its pores carries mainly what cations. The external field causes the movement of the cations and the solvent. The concentration distribution in the membrane pores depends on the amount of the flowing liquid and its flow routes. In turn, these factors govern the resistance of the membranes. The forces that act on the system depends on the state of the system. Means there arise of the auto oscillation, the theory of which has been developed by the Thornhill in 1964, Markin in 1917, and others also. In biological membranes containing enzymes which have cooperative properties, the periodic changes in the state of a membranes may be determined by a non-linear coupling between a transport of the matter and the chemical reactions. We shall consider a simple example. Suppose that enzyme catalyzes the irreversible degradation of a substrate S. The chemical flux is given by J chem is equal to V is equal to d chem into S upon dt, which is equivalent to K E S, where S is a substrate concentration, E is the enzyme, and K is the rate constant. Okay. Uh, suppose Suppose that there is a critical substrate concentration SCT at which the enzyme undergoes a cooperative conformational change that leads to an increase in an activity. The rate constant K increase from Kx to the K2. The dependence of the JCHEM is represented in because of JCHEME, um, or we can say that the chemical flux undergoes a transition similar to a phase transition. The substrates enter the system by the way of diffusion through a membrane at the rate of J differentiation is equal to K differentiation into substrate upon dt is equal to A S naught minus S, where S naught is the concentration of a substrate in the source, which is practically constant. At JCHEME is equal to J differentiation, the rate of change of the concentration. The where S is equal to negative of S chem plus S differentiation, which is equal to the 0. The system in a steady state show the differences between two steady state correspond to the S naught is equal to S dash naught and the steady state. The corresponding to the point of intersection of A of the curve for the JCHEME at the straight line and J at JA at a stable, since with the slight positive changes of the straight concentration JCHEME is more than J differentiation and the substrate concentration drop until the system returns to the point A. We are saying, you can see in this diagram also, this is the J point A, where you can see this is the S naught O, double naught O, and the substrate concentration is behind. Now back to the point. With the negative fluctuation in an with a negative fluctuation in S, the flux J differentiation is more than J chem, and S will increase until the system again returns to the point A. On in contrast, see if the point of intersection B with the JCHEME and J differentiation lies in a region of a curve for the JCHEME and a negative slope, the steady state of B is unstable. To the positive fluctuation of the substrate, their corresponding J JAM is more than JCHEME and the substrate increases up to a point C. At this point, the enzyme undergoes a conformational change. The system passes to point D, at which JCHEME is more than J differentiation. The substrate concentration S fall down to the point E, to which the enzyme undergoes a reverse transition to the initial form. The system moves to the point F. Here S again increases, since JAM is more than JCHEME and the system again reaches to the point C. Thus the system evolved to the hysteresis loop CDEF, to which there correspond to a limit cycle on the phase pattern. A numerous example should be criticized. A numerous example could be cited for such behavior of the system in which the chemical reactions are combined with diffusion. Of course, interest in a in biology are excitable membranes. We have seen that the mathematical models of the nerve tissue is expressed in particular by Hank's-Kin luxury equation. The nonlinear equation of the fourth order. For the purpose of the qualitative study, however, we can reduce the order of a nonlinearity form 4 to the second by eliminating a differential equation for fast components. One of the possible simplified second order models can be constructed and studied by Kerinsky, Iwanisky, and their co-workers work. Uh, Thank you for the today's. Uh,